Hey everyone, thanks for joining us for today's C2 Smart webinar, the last one of the fall 2020 semester. I'm John Patinos, project manager at C2 Smart. This webinar is going to be recorded and uploaded to the C2 Smart YouTube channel with all of our other webinars and recorded seminars. If you have any questions for our presenters, and I'd encourage you to ask many, you can use the Q&A button at the bottom of your screen anytime you want, and we'll have some time devoted to Q&A at the end of the webinar. Today, I'm with two colleagues, Professor Hani Nassif, professor in the Department of Civil and Environmental Engineering and director of Rutgers Infrastructure Monitoring and Evaluation Group at Rutgers University. That's RIME. He's also the associate director of research at C2 Smart and the director of the Bridge Research Program sponsored by NYCDOT and FHWA to provide ongoing engineering, evaluation, and research support. With him is Dr. Jacob Na, Senior Research Associate at Rutgers, also at RIME. He joined in 2011 and his expertise includes structural health monitoring, field of testing bridges, advanced way and motion technology for smart roadways, and advanced cementitious material. Before joining RIME, he was a visiting scholar at Columbia University in the Department of Civil Engineering and Engineering Mechanics. So without further ado, I'll turn it over to Dr. Nassif for adaptation of way and motion standards for autonomous enforcement on the C2 Smart BQE Smart Testbed. Take it away. Still on mute, Dr. Nassif.
Okay, thank you very much, John, for this introduction. And thanks for C2 Smart for giving us the opportunity to share our ongoing work. That this work is, jointly done and sponsored by the New York City DOT. We believe that we are a team. And before I start, I'd like to basically acknowledge a couple of, agencies and a couple of people involved in this. Some of them from a distance, some of them directly involvement. Specifically, the New York City DOT team, starting with Tanvi Pandaya, Don Harrison, and Paul Schwartz, Shane Trotman, Jesse O'Brien, John Anthony Ruccarelli, and Ed Sherry. These are the team that has been very, very supportive of C2 Smart. We have an ongoing, arrangement. It's a ongoing sort of agreement that C2 Smart is supporting the effort from the research side for the New York City DOT, and that has been successful for the last couple of years. I would like also to thank Dr. Azbe and Shri for their support in setting up the test bed that we have along this Brooklyn-Queens Expressway. We are envisioning that to be with the collaboration with the New York City DOT, to be a technology hub for testing various types of sensors, including this that we're going to share today, the wave motion sensor. And I would be remiss if I don't also acknowledge the great support from the New Jersey Department of Transportation, namely for the Bridge Resource Program, which has been really a great effort on their part, and Federal Highway to support our RIME group, and for the last almost 4 years. So special thanks, I think, to Ali Najm, who's the director of the structural engineering, Greg Renman, also the director of the transportation engineering and structural and the structural evaluation, and also special thanks to our colleague, the late Eddie Germain, who passed due to coronavirus during the COVID-19 crisis. So, and especially now our partners from Kistler, Jesse Helminger and Christoph from Switzerland, from Kistler, has been a great supporter of our work, and they are our partners of the center. With this, I'd like to go to the, what are we trying to achieve here? Well, as you know, the overweight trucks has been an issue in many of the states, and Federal Highway mandates a lot of the state to report back the truck weight spectra using weigh in motion data. Weigh in motion, it's the WIM. The trucks are being weighed over sensor as they go at highway speed. However, the effort, to kind of curb these overweight trucks and the enforcement of the legal load limits that are federal limits as well as state jurisdiction limits has been really a very difficult task. It's not effective, as we can see from, when, the side roads, the way stations at the side of the road, many of the overweight trucks, many, what I mean, is percentage that varies from state to state, between 6% up to about 20% in various states. Those are really the most damaging to the infrastructure. So the majority of the trucks are complying. However, there are few percentages, and they're enough to cause damage to roadway pavement, to bridges, and even to safety issues, although we don't have enough data on that. So what we're trying to do with the help of New York City DOT is to establish a site whereby it's a pilot study that we have done. It's a study that we're trying to implement a new standard for autonomous enforcement, meaning that similar to like speed, cameras, where you get ticket if you speeded above this speed limit, the ticket would be mailed to your home. We are trying to figure out some way to make it more ubiquitous to the whole network, rather than making it, kind of a cat and mouse type of situation. So, however, the WIM standards that we have in place right now in the country, in the United States, do not lend themselves to having this jurisdiction or the legislation to allow for such technology to make it happen. So our effort has been over the last couple of years working in tandem with New York City DOT, who is taking the lead on trying to push legislation in the state of New York for this particular site. We are working with them on a pilot study and a test bed to figure out the different types of weigh in motion sensors, different types of cameras, how is that going to be arranged, and how is that going to be handled. So we already established about a year ago a pilot study where we used the high accuracy sensors as well as the regular or the normal piezo type of sensors that are used for screening of weights. But for the accuracy, we're looking to really be very accurate. So we looked at how do we implement that in this project. To do that, we had to look at what has been happening worldwide, what were the initiatives and which countries have implemented this kind of technology, and try to look at the lessons learned and the experiences. And this was a great effort by Kistler that Kistler has been involved worldwide. And they have offices in the United States and a factory in New York and Buffalo. Their feedback was very critical to us to assess this information. Then we realized that we need to have a standard, beyond what ASTM is qualifying and beyond what NIST is doing. And we can look at what can we adapt, meaning that what can we change? How can we figure out the new standard? So we went through the process and we tried, and the important step that we realized was the calibration procedure. And for that, we tried to do it in-house with the help of the New York City DOT. So rather than having, hire a contractor to do it, since this is a matter of accuracy and jurisdiction, we tried to adapt what the fleet of New York City with their help to basically use their in-house capabilities to be able to do that. And then we figured out the rest of the technology. I'll share with you some of the ideas. So for those of you who are not familiar with the area, the Brooklyn-Queens Expressway is a very, very important route that's going through Brooklyn. And, it's about 15,000 trucks a day, basically. And I had the honor to serve on the panel that was appointed by the mayor and commissioner of New York. And we worked with the engineering staff and the administrative staff of New York City DOT with the panel. And the panel came up to some conclusion that this structure is very critical, and it's been built since 1944, but I believe it was finished in the 1950. And since that time, it is a unique structure. It's not a standard typical girder, steel slab on girder bridges. It's a cantilever, as you can see here. I don't know if you can, see my mouth, but you can see there the. Let me try to use a pointer here, or. Okay. So here, the cantilever is a very unique structure, and the thing is that to repair the structure, you have to stop traffic in some ways and close lanes, and that could be disruptive, very disruptive to the traffic. So the DOT has been doing their best trying to keep maintaining it to be in a good condition. However, for a reinforced concrete structure, especially a cantilever like that, and given the level of the overweight trucks that has been traversing over the structure, the deterioration is not slow. So in other words, the panel found out that it will be probably about maybe 5 to 12 years is there when problems will start to appear, and the condition will, after 10 years, the condition will start going even deterioration faster. So something has to be done. And that was based actually on the pilot study that C2 Smart worked on in conjunction and in support of the New York City DOT. So we collected data for a couple of months at that time. Now it's been more than a year. But at that time, when the panel, was making their report, the data was there. So the DOT went out of their way to really collect condition data about the bridge, including GPR, for the deck, finding out what is the actual condition of corrosion of the rebar, of cracking. But at the same time, they kept an eye on the loading, especially the overweight trucks. So from that, comparing the two together, we found out that starting 2025, some sections will have to be upgraded. Otherwise, there will be a problem with the traffic. So the idea, we started the plan about 2 years ago, is to have two sites. One site will be a cantilever, one side will be a pilot study, and the second site will be the one that's going to be coming. This one is called BQE1, which is going to be under this pedestrian bridge here somewhere. And the second one, which is already in place for more than a year now, and is going to locate it on this one. So we started collecting data from this site. And what we have used there as part of our research is to look at what are the types of sensors that can be viable here. And we looked at this is the Kistler sensor here. You can see it, the high accuracy, also durable type of sensors. And we also used the typical, what we call piezo sensors, the piezoelectric sensors, the PVDF sensors. And those are installed in a permanent manner. You cut the pavement and you install the piezo, and we put them in both directions. But in one lane, what you see here, the blue colored installation is for the Kistler, the most accurate sensors. And this one here, the black colored lines are the piezo sensors with the loops. And we have, we were trying to install cameras also on the side, but we have the camera on the side instead of the overhead. And this is some pictures on when this was done. I think it was done, I believe, in October or maybe in September 2019. And these are the group, some of the students and from Kistler, James from Kistler was helping out in putting the sensors. And we had the contractor supported by New York City DOT, their own internal contractor. They did the work. Plus, we had another company that does the cutting. So we were only trying to supervise the installation and made sure everything is working very well. Now, so we have a system, but we want to make it as an autonomous weighing enforcement system. For us to be able to do that, we need a jurisdiction. We need the legislation. And for us to basically support New York City DOT in this endeavor, we needed to look at what are the standards that are applied. And if worldwide, if you look at all the standards, the ASTM E1318, which is kind of regulates weigh in motion sensors, but doesn't really speak loudly and clearly about how to do the autonomous enforcement. And also there is NIST, a new handbook that came out, also does the same thing, but there's no specific language in that one. However, the cost in the European and the international standard, this is the kind of similar to the ISO standard, but this is the International Organization of Legal Metrology. This is the standard that all the countries have been using, and COST 323 was a major initiative in Europe. So we tried to look at all these standards and specifications, and we tried to look at, what is the accuracy needed? Well, we realized that everybody, is looking to have the gross vehicle weight within 5%. So we need to have that high level of accuracy during calibration, and some of them go to about 10% during, the operation or verification. So we looked at them. We did the summary, and in collaboration with New York City DOT, we tried to figure out how do we, if we wanted to use one standard over the other, or maybe a combination to satisfy as many standards as we can, we tried to look at how do we calibrate. So that was the initiative that we wanted to do. So we looked at what is the different systems, compliance. How do you comply with all these 4 specs? So the ASTM asks only for 2 trucks. So there's a little bit of variation. If you look at those standards, the European and the international standards are more specific, more, I would say, I don't want to say strict, but more elaborate on how you're going to do it. Whereas the American standards, including ASTM, I think needs to have modified, needs to be changed to accommodate for this endeavor, for it to be able to happen. So for ASTM, specifies you need 2 trucks. For NITS, you also need 2 trucks, one class 9, which is 5 axle, and one class 5, which is like a box truck, a small one and a big one. But those, the ones with the green, means that you have to have a minimum of those. Whereas the cost, you have to have also those that are, mandated, and then they are specified. So we tried, in our calibration, we tried to look, actually there is a difference between our truck configuration in the United States and between the slightly different in the European configuration, or other international in China or in South Korea. There are differences. Those are the countries that have implemented this autonomous. There's a slight difference. However, we try to adapt those differences and keep our trucks to the federal highway classes that are mandated in this country. So this is my introduction, and I'd like to Chekuk, because Chekuk and the other and our colleague Panglu, they were the ones who are involved in the implementation of this endeavor. So I'd like to invite my colleague, Dr. Chekuk, now to take over and present that work.
Okay. Thank you, Dr. Nassif. Do you see my screen? Okay.
You're in speaker mode right now. You're not in full presentation mode.
Okay, so this way. Is this better?
Yep.
Okay, sure. Okay. So as Henny mentioned, that we were trying to use the trucks that is available from New York City DOT. So we have selected 5 trucks among different trucks, and from the New York State DOT. The truck fleet, and for the calibration, we need to measure the axle and wheel load, and also the gross vehicle weight load, and also the extra spacing in advance, so that we can get the accuracy of the WIM system. For that purpose, we visited to the New York City DOT Harbor Street Yard and get the axle and wheel load measurement using the portable scale, and the gross vehicle weight using the static scale, and also measure the extra spacing using the time measure. And those are the trucks that we have used for our calibration process. So there are 5 trucks, as I mentioned. There are we call it R1, 2, 3, 4, and 5. And R1, 2 are, as Henny mentioned, this is the class 9 truck, and those comply with the ASTM, COAST, and OIML. And also one of them comply with the NIST. And other trucks that we used are the one class 6 truck, which is the dump truck, as you see here on the left side. And we use other class 5 trucks here in the middle on the right side. And class 5 is normally like 2 axle single unit truck. And the right side is this one is actually class 3 truck. But if the federal highway classification states that if the wheel axle has a dual tire, that will be classified as class 5, not class 3. So those are 5 trucks that we use for our calibration of our process. So for this calibration, there are kind of 3 steps. The first thing, we need to calibrate. The words are the same, but actually the calibrate here on the left side, the blue one, calibration means to obtain the factor of each sensor. And then this verification and optimization is the way that we can optimize the sensor factor for different trucks type and different the weight and also different speeds to improve the accuracy for the use of autonomous enforcement. So during calibration, and initially, as I mentioned, we did the calibration in September 2019, and we got a good factor at that time. We got about 10% of accuracy. I mean, the error using one type of truck, and we had the factor. We had the factor in the past, but as time passes, it has been over 1 year, and we got the new factors, and the factor changed from like 1.12 to 0.83. Something is reduced, something was increased. Because of this, using the factor that we obtained in 2019, the error was about, using that factor, the error at that point when we did a recalibration in October 2020, the error was about approximately 15%. Based on that, we need to recalculate the factor, and with the new factor, the error falls within like 5% for one type of truck. I said one type of truck for the calibration is because in general, the WIM system can take only one factor for each sensor. You cannot accommodate different factors for different type of truck or different weight of the axle or gross vehicle weight. So we use only one truck to get this factor, and this is how this is the accuracy that we got. And then using other type of trucks, I said we use 5 different trucks, R1, 2, 3, and 4, and 5, and from class 9, class 6, and class 5 trucks. Between trucks and between weights, there are some different interaction between the vehicle and the sensor, and this verification and optimization process is something that we can do to improve the accuracy of the WIM. One thing that I want to mention here is that during verification, we try to run the cases in the middle of the lane, which is center here, or on the left side of the lane, or the right of the lane. This is according to the ASTM and OIML as well as the COAST. And the reason for this is that when, because the pavement has some rutting in general, because the pavement is not perfect in every place. And when we install, and especially for this size, the pavement was not was well maintained because of the overweight truck. There are some severe rutting along the roadway. So here on the right side here, the blue one shows the quartz sensor, and the black one shows the epoxy when we install, because the sensor is straight, you cannot bend it at all. So when the wheel passes in the center of the lane, the forces applying to the sensor is different from when the wheels are passing on the left or right side because of the epoxy. the force will be much lower when they are running on the left or right side compared to the center. So all those things has to be accounted during the verification and optimization. Also, another thing need to consider is about the speed, because the speed will, depending on the speed, the accuracy also varies when it's low speed or high speed. And also the gross vehicle weight or axle weight, if it's light, there's more interaction between the vehicle and then the pavement, because it bounces up and down. Versus when it's heavy, then it is not as much as like that. So we need to those things should be considered in the verification and optimization process. And we work together with the Kistler, and with their help, we were able to optimize the WIM system to get the high accuracy for the autonomous enforcement. So this is the calibration test we did. Because of the traffic, we did like from 8 a.m. until 6 a.m. without any break. The truck ran from like 10 p.m. until 4 or 5 a.m. and we had stayed there 1 or 2 hours before and after to prepare and to wrap up our work. And those are the pictures of the student. They worked on Thales, Chan, and He, thanks to them. And this is picture of the field that we worked. There's some computer and then the field, the box that we have all the batteries and systems. And this is the calibration process. So this is the R4 and R5 capacitors, and another 3 trucks are helping us to control the traffic and etc. So we did like this run almost like every hour. We had about 3 or 4 runs. And we had for about 6-hour run without stopping. So we had about 70 run or something. But as Henny mentioned, that we had only 1 lane for the quartz sensor. That's our main target. And other ones are to also calibrate other the PVDF sensors in other lanes to collect the traffic information. So here are the results. After calibration and verification, as well as the optimization. So this is a summary of the results. Then there are 5 trucks from R1, 2, 3, and 4, and 5. And we are targeting ASTM type 3 at 95% compliance of the all gross vehicle weight, single and tandem. So ASTM type 3 requires about 6% maximum gross vehicle weight error at 95% compliance, which means out of 100, 5 can exceed the 6%, but 95 runs out of 100 should be within 6%. And the same applies to single 15% and tandem 10%. And if you look at the average gross vehicle weight, they are very small. It's like less than 1% in general, or 0.01%. And this is because between runs, some runs are overestimated and some runs are underestimated. So if you average them, it will just balance out. So you have to look at what is the maximum error that we got from this calibration testing. So among those, gross vehicle weight error falls within like 4 or 5%, and single axle is about 12 or 13%, and tandem weight is about 8%. This resource is very good, and they all comply with ASTM type 3, and also NIST, of course, because this is not really a standard yet. It's not like out yet, and it's not really standard for the enforcement, so it easily can comply with this. And OIML and COAST, we almost got that point to comply with their standards. Gross vehicle weight, we complied, and tandem, we almost complied. Although the cost is 7%, we got about 8% maximum. And the single weight is we are a bit far from what they are looking for. But again, this is 95 percentile percent compliance. So this 12% is just 1 or 2 cases, and the majority of them will fall within 8% of single axle weight error. So as a summary for this quartz sensor calibration, So core sensor is able to comply with the accuracy requirement for all standards. Not every time, but we are capable of obtaining that accuracy. The maximum error for the gross vehicle weight is less than 5%, and the maximum error, wheel, axle, and tandem are also all comply with the ASTM Type 3 for this autonomous enforcement. As you see here, compliance for gross vehicle weight, single, and tandem, that are in 100% compliance with the Type 3 case. And the wheel load, they're out of like 120 wheel load that we measure from all the trucks and all the runs. 2 or 3 runs were out of the 20%. It's a 20, almost 22%. But that's 99% compliance. So we are all good for the core sensor to use the autonomous enforcement. And calibration tests could be performed using one Class 9 truck, as the calibration factors cannot cover different type of truck. But the verification process and optimization process can help improve the accuracy of the weighing motion system. And one thing that I want to emphasize here is that we, as I mentioned, there were some rotting on the pavement. However, the occurrence, and that this accuracy could be improved if there are some repavement of the site. However, without even doing so, we were able to obtain good accuracy for the future use of the autonomous enforcement. And other sensor calibration is the PVDF sensor, which is less accurate than the core sensor. As you see here, we have 6 lane of sensors and 3 on the south, the state line bound, and also 3 for the Queens bound. And again, for this system also, it only can calibrate, get 1 factor per sensor. We use only Class 9 trucks to obtain the calibration factors. So these are the results. As an average look at, similar to what course showed, it is like less than 5% or maximum 10%. It looks we are okay with it. But if you look at the maximum value of the error for 2 type of R1 and R2 truck for gross vehicle weight and single and tandem, they are really far away from what the ASTM Type 3. So we were trying to target Type 2 target, which is 15% of error for gross vehicle weight, 30% for the single, and 20 for the tandem. And again, this OIML cost, we are not able to obtain, comply with it. So this is a quick summary of that test. And the ASTM, we were targeting 95% compliance, but we only get about 70 to 80% of compliance for the gross vehicle weight, single and tandem. So these PVDF sensors are not really, is not able to comply with these standards. We are marginally were able to comply with Type 2 accuracy. And when we look at the accuracy of other type of truck, the Class 5 truck, which is the smallest truck, is really hard to get the accuracy because it's too light, and the PVDF sensor is not really sensitive, to get good measurement of the truck weight. So all of this effort, we are aiming to get to develop the autonomous enforcement practice. So this is the scheme of what we are trying to do here. So from the truck, we get the measure from the core sensor, and in the system, it can spit out if it is violated per any way. We can specify the axle weight or tandem weight or the gross vehicle weight, even speed or etc. And if it's violated, then we can send the trigger signal to the camera that that is capable of identify the license plate of the vehicle. And then we match between the weight of the truck and also the license information, and then we save that into the database in order to start work. I mean, to do some post processing of the ticketing and other things. And to prove that, we need to test this AAPR with this the automated license plate recognition system in the field, how it works during the daytime and also during the nighttime. And we found that with the program that are available on the market, and also with the typical camera that are on the market also, we were able to capture the truck and with the license plate, and the license plate is readable even during the daytime and also during the nighttime. So we kind of prove our concept of how to do this autonomous enforcement, and we are keep working on that to how to compile two databases from the WIM and this ARPR in order to make some automation in ticketing the overweight trucks. So what are the practice that has been done thus far in the US, also in the other countries? And one special project in Indiana, they have installed this quartz sensor near the weighing station, nearby weighing station. So this clean road is their test site that they have repaved whole the pavement, and they installed it. So they make a brand new pavement with the quartz sensor. And after this site, just as within a mile or so, there is the weighing station. So what they did is, whenever the truck passes here, they measure the weight, and they guide the trucks to measure their gross vehicle weight and axle weight at the weighing station, and then they compare between them. And they tested for several weeks in 2000, I believe 2017 or something, and they got good the results. They within 5% error. Almost 100% of the cases they got a good accuracy. So this has been done there, but they haven't really put this into registration or to make it an active site yet. And we are trying to do that in New York State, New York City DOT at this point. And there are other countries that has been working on this one. And in Europe, there are many countries, Czech Republic, Hungary, and Russia. They have already initiated, and they're already operating this type of the autonomous enforcement practice since 2015. In China also, they are already starting in 2016. And they're all looking for about 5% accuracy, which we were able to obtain, obtain from our site. So, and the last thing that I want to mention is about our new smart roadway testbed, which is called BQE1. As Henny showed earlier, along this triple cantilever section, northern portion is the BQE2 that I showed earlier that we just recalibrated. And this BQ1 is the south portion of that segment. So for this side, we are trying to evaluate what accuracy we will able to get it before even installation. So we did some preliminary site evaluation. Where are the cracks and how is the rotting? How severe it is, and etc. And based on that, we propose to install the quartz sensor on all the lanes at some of the section of this roadway, and this effort will be continued in 2021 as the weather is getting better. We start to evaluate all these lanes and install all the sensors, and with the ALPR camera to capture the license plate and start working to tune the system for the autonomous enforcement. So this is the summary. Yeah, so based on all this effort, we were able to obtain like 5% of gross vehicle with error that comply with ASTM, NIST, OIML, and COAST, all the standards. And we kind of developed a practice that we can calibrate the system that complies all this standard in the US and Europe and also internationally. And the pavement condition is very important for the weighing accuracy. However, the system could provide sufficient accuracy when the pavement condition were not that perfect. But as you said initially, for the calibration, the factor drifts over a year between 2019 and 20. So it is really highly recommended to calibrate the system every 6 months, preferred, or maybe every 3 months in the spring, summer, fall and winter, if this is intended to use for autonomous enforcement. And this autonomous enforcement is a new procedure, and standard calibration procedure and practices are required to support autonomous enforcement and its registration. And that's it for my presentation. Annie?
Thank you, Chico. Yeah, I mean, the summary of this is that this effort is really, really needed in the United States to start thinking about other ways to implement enforcement. And I believe other countries have found out that this is probably the most effective way. And you know, as we have tried to show, without you know, treating the pavement or repaving or micro milling, or we use the pavement as is, and there was a little bit of rotting on those pavement. Even with those conditions, we were able to achieve the accuracy that is required, at least on the gross vehicle weight. And that could be what the enforcement you know, could be, because you know, the legal load is about 80,000 pounds. So and we're not trying to, you know, catch every truck, you know, especially for example the class 5, the accuracy on those, you know, which is the small box truck or the small pickup trucks, those, you know, are not the offending, you know, those are not the damaging trucks, you know, on bridges and pavements. So we're trying to look for those big offenders, you know, mainly the 3-4 axles and the class 9, which are the 5 axles. Those are the ones that go overboard. And if we can achieve that, and at least, you know, send a message to the you know, and I know, you know, we had a lot of forum where we invited the trucking association, and believe it or not, the majority of trucking association, they are complying. It is the you know, the individual or the mom and pop who own the truck, and they feel that economically it is to their advantage to overload the truck. But I think that is changing a little bit. We want to work with the trucking associations, the long haul and the short haul, to basically make this a kind of a real project where different states could really start thinking about the implementation. But I really think that one of the important elements for this is really what New York City DOT has tried to do, which is push a legislation through the state. And there is a bill now that's being discussed, and hopefully it will come out. This is really a prelude effort that needed to basically make this happen, because without jurisdiction, without legislation, this technology cannot be really effective. So I think with that, I open the floor with questions. I think this is a great project. Thanks for C2 Smart for always supporting this, and for New York City DOT for all the meetings and their effort. They went really overboard to help us out and make this happen. So we really appreciate everybody's involved. So are there any questions, or I'd be more than happy to answer them.
Yeah, please feel free to use the Q&A button at the bottom of the screen, and I'll start to read them out to our presenters. I guess, Professor Nassif, I'll just start out. So in like what is your vision for autonomous enforcement in the United States in like 5 years time, or in 10 years time? If you see other places besides Indiana and New York adopting this technology in the near future?
I think so. I think this is a good time. I mean, because you know, the funding for repair and rehabilitation, all the states have some priorities. It's very difficult to basically allocate money for continuous repair. Plus, you know, when we design bridges, I'm talking about bridges because that's my training. I'm a bridge person, but that also applies to pavement. We design pavement for 20 years, but we design bridges for 75 years, but their service life is becoming probably, 50, and bridge decks, it's about 40 years. You start having problems, and so you are cutting off the age of the bridges, and that's the wear and tear, from the environmental condition. But the fact that you have overloads is also make the problem worse. We did a study with my colleague Dr. Osby on the impact of overweight truck for New Jersey, and this is kind of an example how the other DOTs now are doing it. We used the WIM data, and we correlated the damage from the overweight trucks to the bridges and the pavement in the neighborhood of these WIM stations. And we could see the correlation very, very clearly, that the overweight trucks and the damage on the bridges are correlated to each other, and even the pavement. So the only way, and police units are trying their best. I mean, I know we have in New Jersey, we have a good police unit from the Turnpike works with the DOT state police, and they chase these overweight trucks. But the trucking network kind of avoid these enforcement units. So it's like a cat and mouse type of situation. I think this will be a standard. Hopefully, our effort, we are putting it out there. Thanks to New York City DOT, they're very forward-looking, including from the commissioner down and from the mayor down, to try to help us and help the engineering community at large show that this is feasible. And I believe if we were doing the site with a new pavement, with all the regulations that we need to do, there's definitely the accuracy can be across the board. So I from here I'm making a call for everybody who's in charge of this. Try to do a pilot study in your state and see if we can help out. I mean, we're putting our information out for that reason, because we wanna kind of, maybe we are preaching to the choir, but I think for our forum that Cito Smart has sponsored a couple of years now, we invite all the stakeholders, including the trucking association. We don't want to work in an adversarial position. We want to work with all the stakeholders, including the trucking association, to make this happen. So I guess, within 5 years, this is going to happen. Once legislation is passed, I think the technology is there. I mean, we've shown it. There are other vendors who also do probably, as good of a job as we did. But what we're trying to do is, number one is the legislation, and number two is the standard specification. What are you going to follow in this country? They are, as we said, we narrowed it down. So now it is the job of us trying to suggest something for ASTM or for the NIST, and have a standard in this country that can be followed and adhered to. Those are I think the blocks that we need to really clear out of the way.
Okay, so we have a whole bunch of questions that have just come in, so I'll try to get to all of them. The first one I'll read out here is, do you foresee a need of a standardized WIM weigh in motion system certification process?
Absolutely, and this is a very good question, and this is our effort. We're trying to do that, in this project, as much as with the resources we have from Cito Smart and the major effort from New York City DOT. We're trying to do it in-house so that, each agency would have their own fleet. They don't have to go outside to do that. So this is what we are trying to do. Kind of, we're borrowing the best practices from other countries and trying to implement them given our truck types and configuration. I think this is a key. The key is to do the specification. I'm hoping that at the end of our project that the Cito Smart Center is taking the lead on that, with the leadership we have. I think we are putting a lot of funding into this to make sure that this will happen.
Okay, so similarly, have you experienced any guidance or push coming from USDOT or at the federal level to push states to do this, to adopt this kind of weigh in motion technology?
The push, I think the Federal Highway has a mandate on each state to report back their live load spectra, the truck weight spectra, because these trucks are using federal highways, interstates, and there's funding from Federal Highway. So they want to make sure that everybody is complying with the effort. And there is a chunk of money from Federal Highway to be dedicated to enforcement. But the amount that's available, given how how you know, I mean, overarching this task, the amount of funding available for enforcement is really dismal, in my opinion. So, you know, there's no clear effort from federal highway. I think states are taking, like Indiana project, for example, they started like maybe 1 year. We were always advocating that, but Indiana had a great project where the state took the initiative with their enforcement police. So I think this is now a state initiatives has to be, there's no clear, federal highway would like to do it, but the implementation is on the shoulders of the states. So yes, I think we need, from the feds, we need to lobby for a legislation that can change the method of enforcement, similar to what New York City DOT has done. That could be a good example for how each state, you know, if they could legislate particular site. It doesn't have to be all over the state, but particular sites where we're seeing a lot of percentage of overweight, that could be handled in that way. And that could be very effective, in fact.
Can you talk about the accuracy difference between the sensors, the piezo and the Kistler sensors?
Yeah, exactly. The first, we did that about a year ago. We compared the accuracy. The sensors that are piezoelectric sensors, they're not really meant. That's why ISTM categorizes them as type 2. So the limit on the accuracy by default is different. Whereas the Kistler sensor, it's much more durable, and you know, it's kind of independent of the pavement. It has its own encasement. So temperature and also the braking force or the expansion and contraction doesn't really affect the sensor a lot. Whereas the piezo is affected by temperature fluctuation of the pavement, daily and seasonal. So we accommodated for that. And even when you do that, you still have a big margin of difference between the two. As you saw here in our case, I think you're talking about 5%, within 5% on the gross vehicle weight, but within 10%, and you can't get it most of the time, especially if the sensors are old. So you need to calibrate more often, you know, and correct for that. The piezo sensor is about, you know, shelf life 2 to 3 years, whereas the Kistler, you know, a lot of DOTs have been installing them, and some of them have been working for 5 years, and so they should last longer than 5 years even, you know. So there is a difference between the two, but there's also price difference, you know, like the one sensor from Kistler is probably 10 times the sensor from the, but in terms of the longer life cycle cost, and in terms of the benefits, especially in the autonomous enforcement, we can't go in other direction other than the using the quartz sensor, the Kistler sensor.
Okay, so you sort of answered this next question, but it's just in case you have anything else to add. What is the expected life of a well-calibrated weigh motion system, and how will it be monitored?
Yeah, if we are going to end, excuse me about my voice, I'm under the weather for the last couple of days. If we are going to talk about enforcement, autonomous enforcement, you have to be within the standards, and that, I think, in our opinion, probably it's going to be about 3 to 6 months, depending on the site. If the site is a new site and has a new pavement, I would say 6 months should be sufficient. But if you are using, like we are, if you are using the pavement as is, I would suggest that checking the system every 3 months. We had some programming is to figure out when is the site drifting in terms of accuracy. We can always do that, and many of the systems are programmed to do that. But in particular, this would be an indication. You know, it doesn't have to be periodically, but it could be on demand. For example, if we look at the axle loads, especially the front axle of a 5-axle truck, it's usually constant between, let's say, 10 to about 13, 14, with an average of 11.7. That's what Federal Highway mandated. So if you look at that front axle, that's usually constant. And if we calibrate based on that, we can check that periodically, and we can see if it's drifting down, it means the calibration factor is drifting, then we have to interfere and do the calibration. So I would say, as a rule of thumb, every 6 months, if the pavement is new, but every 3 months if the pavement used with some rutting or some roughness, to make sure that the calibration factor within the limits.
Okay, so
Patty, I think our friend Andrew Ludasi from NJDOT is asking a little sarcastically, who's going to calibrate the system every 3 months?
Well, if it is enforcement system, I mean, I'm not talking about a general WIM system, but if it's a system, that's used for enforcement purposes, then the certification is needed. And to certify that, you have to go through the effort of doing it. And that's why we wanted to use the in-house, trucks, and it takes only a day. And if the agency has its own resources to do it, I think they will do that. I'm not talking about the piezo sensors uh, and as I said, because the calibration is not only about the sensor, but it's about the rotting of the pavement, the temperature changes from seasonal. So 6 months, if the pavement is new, should be more than sufficient, usually. But 3 months, if the pavement, like our site, I would not trust it more than 3 months, for example.
Okay, I think we have time for just one last question if we could squeeze it in. So do you think it is better to incorporate weigh in motion and other structural health monitoring as part of the design of a new bridge project? If yes, what tools would be needed to implement the system and collect this amount of data? So like a smart bridge from scratch.
Yeah, definitely. We've done a couple of projects as part of RIME over the years. We are really, this is the heart of our work, is when we combine what we call SHIM and WIM. Because, from SHIM, the structural health monitoring sensors gives you about the resistance of the bridge, meaning, the response. How does the bridge respond? Strain, deflection, vibration, and even durability side of it. We put sensors there. However, if you don't put a WIM sensor to know what are the loads that are causing these conditions, then part of the picture is not known. So we definitely recommend having WIM and SHIM hand in hand, because then you have the idea about the load side and the resistance side. As you know, the code in bridges, the LRFD design code, is built on the reliability based approach, which needs statistic. How does the load vary? It's a parabolic change. And how does the resistance vary? So definitely having both, it would be a good recommendation. But for enforcement purposes, you really, I mean, if putting the WIM, if you have a shim on the bridge and the bridge is old, yes, definitely that would be to keep an eye on the loads and keep an eye on the, but as an enforcement system, it doesn't have to go with the bridges all the time. It could be any other site outside the city or inside the city.
Okay, so I think that's all we have time for. Perfect timing. Just a quick note before we wrap up. If you've enjoyed this webinar, please follow C2 Smart on Twitter, join the C2 Smart LinkedIn group and the mailing list. It's been a great year transferring the results of research happenings at C2 Smart, and I hope you all join us for our next set of webinars in 2021. Have a happy holidays to all, and thank you so much, Professor Nassif and Dr. Na, for presenting this research, supported by NYCDOT and USDOT.
Thank you, and I would like to thank our team and New York City DOT again, and NJDOT, because partially they had a hand in this. And I want to wish everybody happy holidays and greetings for all the holidays this coming up.
And thanks for bearing with us, even though you felt a little under the weather.
Yeah,
appreciate it.
sorry, I apologize.
Feel better.
Thank you.
Take care.